Alright, in this video I will comment quickly on the way we solve question 61, part 2. Part 1 is nearly identical, so we will focus on part 2. I would like to emphasize that before you read the solution, you have to read my notes and listen to my comments on a subject which is called map of the boundary. This subject is available for Navigator, map of the boundary, and there are actually, right now you don't see it, but there are video comments next to in a list of resources for that topic. Okay, so look at the screenshot and listen to the comments if the screenshot is not self-explanatory. Now, the key to our approach to this question will be showing where the boundary of this set goes. Of this set. So we will look at the set. This is a square. This is a set in part 2. It's a unit square. And we will focus on where the boundary of the set is taken by this map. Before we can do that, we have to confirm that this map is injective. That's a critical condition which appears in the map of the boundary result. You see, the map's supposed to be injective. That's what it is. And we're about to test this for this map. I'll zoom in a little bit and I will do my test. So if I test that my function is injective or my map is injective, I do this. I assume that my map has 2 points which deliver identical values. And from there, what I'm going to do is this. First, I will observe that this implies the following two relations. This implies the following two relations. This is from my map. Then I will observe that the second one, if you cancel one on both sides, will give you this relation. Given this identity known from the high school, which is called difference of squares, we can actually use this identity here and here on the left and the right hand side and actually cancel these identical factors. Given that these factors are non-zero, we can cancel them and then we'll have this relation. And then it's not a difficult argument to conclude that these two, they imply that actually points x1, y1 and x2, y2 are identical points. Okay? So what we see in this line of argument, that this map is injective everywhere except this line. This line. And that's a good news for this question because our square is entirely away from this line. So we can use this result which tells you that the boundary is mapped to a boundary because within this square we don't have points where my map is not injective. Okay? This is in sharp contrast, in extremely sharp contrast to part 3, where we have to map this set and this set. It's a half plane, and that half plane actually contains this line as its boundary. Hence, for part 3, this method is not available. That's why for part 3, if you go to the Navigator, for part 3 of question 61, I developed completely different solution, and you encouraged to read this. That's why for part 3 we cannot employ this method of mapping boundaries to boundaries. We have to come up with something else. And this hint in part 3 tells you what to do. Now back to part 2, sorry. So we're going to map boundary to boundary. So we just discovered with you that my map F is injective everywhere except this line x plus y equals 0, so we can use it in the current circumstances. So we're going to map the boundary first. That's what I'm planning to do. So we're going to split this boundary in 4 subsections, these 4 straight segments. They represent 4 different parts of my boundary, and I will parameterize them all 4 like this. Look at this. This is part A of my boundary, and that's how we parameterize that. And this is a part B of my boundary, and that's how we parameterize that. This is part C of my boundary, And that's how we parameterize that. The last part D, this is a parameterization for part D. Every time parameter t here between 0 and 1. So now what we do, we take these parameterizations and we plug them into my map. We plug them into my map, this map. So for part A, I'll have this result. That's how the image of this parameterized curve will look after you apply the F map. If you now solve for, this is x and this is y, if you get rid of t, you end up having this equation or this relation with x, which is a parabola. And the y will have a confined range because t between 0 and 1, t plus 1 will be here. If you do similar tricks for the rest of the parts of the boundary, like the B part is taken by your map to this parametric curve, or if you convert this to Cartesian equation by reading of t, this is a 1. Both of these functions, by the way, parabolas, that's where we need our recognition skills. Y value between 2 and 3, because t between 0 and 1 still, and t plus 2 between 2 and 3. Part C, that's how part C looks after map F is applied to it. Again, it's a parametric curve, but if you convert this to Cartesian, by reading of t, again, you can spot another parabola. And again, y will be within range 2, 3. Finally, part D, that's how you parameterize the image of part D of the boundary. And again, this resolves to a parabola. And y is like this. I plotted all of these parabolas. Here they are. All of these parabolas. This is a parabola with the vertex here. It's the with the branches going to the right. This is this parabola. This one. This one is down here. This one is this one, and the last parabola, part D, is this side. Okay, all these parabolas, they will look like this. We don't need the entire parabolas, we just take sections of them because of these constraints. Now, the final part, which I have to mention, is this. If I take a point in the middle of this square, half-half, and I apply my map to that point again, this map, it's direct computation, the result will be 0, 2. It's this point, right in the middle here. So one point inside my square goes into this point inside this shape, spade-like shape. Now, if I switch back to this result, right here, that's what we need to mention now, because this result tells you that interiors go to interiors. What I mean is this, by what I'm trying to say is that any other point within the square, even if we're not going to compute f for those points, they will also go inside this spade-like shape. Because if you assume for a second that some bad point or rock point in the square goes outside, given that the half-half point is inside and this rock point inside and this set is path connected, you can always connect here these 2 points with the path entirely within the square. And then, according to this result, such path will have a point on it, which will cross the boundary, and that's a contradiction. Hence, the entire square goes into the interior of this spade-like shape, and that's how you find the image in part 2. This is it. Thank you very much.